Hello and welcome to section 5.3. We're going to be talking about how to name and communicate about chiral carbons in molecules. And to do that, we're going to use a naming convention system for organic chemistry called the Kahn, Ingold, and Prelog system. From now on, we'll just call it the CIP system. And that's the system designating whether chiral carbons are either R or S. Those are going to be the two names that we use, R or S. So this is going to be really important because we're going to be able to draw molecules. And let's see, if we had this molecule, it's very simple. This molecule has a molecular formula of C4H3689 Br. It has one chiral carbon because the hydrogen is on a dash. So we're going to be able to say whether that chiral carbon has a configuration of R or S. And we're going to be able to identify this in a systematic way. And in addition, we're going to be able to say how to use these in a systematic IUPAC name. All right, so let's do an easy one, or a very simple one, I should say. So if we have a carbon, and that carbon is attached to a hydrogen, OH, let's draw it a different way, because I've been drawing it the same way each time. There we go, here's a wedge over here. This will be a chlorine, and this will be a CH3. In order to determine whether something is R or S, we need to do a set of rules each time. So the first rule is, obviously, do we have any chiral carbons? Yes. This one. Okay. Second, we're going to follow a series of steps here. The first step says to designate the priority of substituents. Priority means, in this case, what is the atomic number of the atoms you're dealing with. So what you need to do is look at is figure out which molecule or which atom has the highest atomic number of the substituents. Hydrogen has an atomic number of 1, right? Carbon has an atomic number of 4. No, it's 6. I always forget what carbon's atomic number is. Let's see. Right, so it is 6. Oxygen's is 8. And chlorine's is 17. So you just take the biggest number, which here is 17, and you give that chlorine the number 1 priority. Biggest atom, highest priority. Next, we have the oxygen. That substituent is 2. The carbon makes it 3, and hydrogen makes the 4th most important, the least important substituent. Now, we need to rotate substituents so that we can put the number 4 on the dash, meaning going away from us or behind the molecule. So to do that, what you're going to do is you're going to hold one of these substituents constant, and you're going to rotate the molecule otherwise, much as you would do a top or maybe like a little paper umbrella or something. So if you were to imagine that we were going to place our fingers on this OH here, and we're going to hold that steady so that we can rotate the rest of the molecule either this way or this way. Our goal is to get the hydrogen on the dash. And just as a little side note, that means that obviously we cannot hold the hydrogen steady, because if we hold it steady, then it will not move. I'll try and do a tutorial later with a molecular model kit. That way you can see this in action. But we're going to use our mind's eye in this case to do the rotation. So if we rotate, let's say clockwise, or rotate from the Cl towards the H, rotate. Then we end up with, so here's our carbon and our OH, which was the same. Remember, we kept that stable. So the chlorine, where it was on the wedge, is now going to be on the normal bond on top. The methyl group, which was once on a dash, is now going to be on a wedge. And the hydrogen, which was once on the normal bond on top, is now going to be on the dash. Great. So we have our substituents. 1, 2, 3, 4 in the proper place. Now all we have to do is rotate from 1 to 2 and determine whether that is a clockwise or counterclockwise rotation. So to do this now, imagine that we're going to make a Newman projection on this carbon. I think this is the best way to envision that of what you're seeing. So if the Newman projection is this way, where you're seeing that carbon, that means now your carbon is in the middle, right? And now you have something coming up and two things on the side, because the hydrogen is in back. Remember, we don't see that. So now you have your chlorine there, OH here, and CH3 here. 1, 2, 3. So now it should be very easy to tell how to rotate this molecule from 1 to 2, and it should be clear that that should be a clockwise rotation, which means this should be R. So that's our steps, remember. First, assign priority of substituents. Second, rotate everything to put the hydrogen on a dash. Third, make your Newman projection and determine if the rotation from 1 to 2 is clockwise or counterclockwise. Remember, in doing the priority designation, you need to use atomic number to do that. Or in other words, which substituent is bigger? Okay, and there can be tiebreakers when you do this. What that means is if two substituents have the same number, oh, I cannot type, then you go to the next atom. Let's do one of those together, where you have a tiebreaker. So let's say that you have these two molecules. So you have this versus, okay, so if you have this molecule, similar to one we looked at above, remember, there is one chiral carbon because there's a hydrogen in the back that we didn't show. Okay, so the first priority obviously is going to be the chlorine because it's a number of 17, and the last priority is going to be the hydrogen because it has a molecular weight of 1, or an atomic weight of 1. But the other two are both carbons, which means they are both 6. So you need to do the tiebreaker round and list each substituent on the carbon underneath. This is what your book does, and I think it's useful, so I'm going to do it the same way. So each carbon is attached to, on the left, we'll do this one in blue, and on the right, we'll do that one in red. Okay, so the blue carbon, we have 3 hydrogens, right? And the red carbon has 2 hydrogens, but another carbon. So while the first 2 cancel out, the red is the winner with the carbon bonded to it. So that means it gets second priority. And the blue carbon gets the third priority. Another thing to note is that double bonds count twice when you're doing this tiebreaker round. So if you were to have, let's say, a very similar molecule, here, now you have 3 molecules that could be in the tiebreaker, because while there is a hydrogen on a dash, and we know that is going to be number 4, the other 3 are all carbons with 6 atomic weight, right? Oops, sorry. So each of them need to do a tiebreaker now. So we can do that if we just assign, let's see, the one on the left will be blue, the one in the middle will be green, the one on the right can be red. So the blue carbon has 2 hydrogens and an oxygen. The green carbon has 3 hydrogens. And the red carbon has 2 oxygens, or 1 carbon. Yeah, 1 carbon and 2 oxygens, right? Okay, so in the beginning, the red carbon wins. Oh wait, actually, this was a hydrogen here. So it should have been a hydrogen. Sorry. So in the beginning, they all tie, so nothing happens. But because there are 2 carbon-oxygen bonds, the red carbon, it wins to get number 2. And the blue carbon wins to get number 3 because it has 1 carbon-oxygen bond. Which means, oh, sorry, 1 and 2. That's number 1, that's number 2, that's number 3. And put that closer to the carbon so it makes more sense. There we are, which means that now we know the priority of this molecule. And if we were going to use the IUPAC nomenclature in making a configuration, so we can just use the same molecule here. Let's bring all of this work down with us. There we go. So we have the priority here, and we don't have to do any rotating because the hydrogen is already on a dash. So we can just make our Newman projection to determine how we should rotate the molecule. So again, we have CH3 up here, this double bonded O with the hydrogen over here, and this molecule, or that part of the molecule there. And remember, this was 1, 2, 3, which means we rotate clockwise, which means it's R. So in naming this molecule, we would call this, let's see, so the parent chain here is, looks like 1, 2, 3. Do that in green. 1, 2, 3 carbons long. or we could do 1, 2, 3 carbons the other way, but the chiral carbon is on the second carbon, so it would be called 2R. So let's do a slightly easier example that has naming that we actually know how to do here. So here, we're going to do this molecule. Hydrogen there. We'll give ourselves another carbon there. And we will give ourselves another carbon here. There we are. Okay, so let's do this. Let's not only find the number of chiral carbons, which is 1, but let's also give this an IUPAC name, which means that we need to determine the configuration using the CIP system of that chiral carbon. So to do this, remember, we need to identify and assign priority for each of the substituents. Hydrogen, always lowest priority at 4. But we have 3 carbons that need to have a tiebreaker. So let's give the left one a blue. Let's give the middle one a green. Let's give the right one a red. Okay, so the blue carbon has 2 hydrogen bonds and a carbon. The green carbon has 2 hydrogen bonds and a hydrogen, so 3 hydrogen bonds in total. And the red carbon has a hydrogen bond, right, and 2 carbon bonds. Okay, so they all don't have a third carbon. It's all hydrogens there. And the first one to have something other than hydrogen is the red carbon. So the red carbon gets the number 1 designation. The next one to have something other than hydrogen is the blue carbon. So it gets the number 2 designation, leaving number 3 up on the top. All right, cool. So now we need to rotate this molecule to get the hydrogen on the dash, right? How are we going to rotate this to do that? Why don't we hold number 2 constant and rotate everything else from number 1 towards number 4 to do that? All right, so if we do our rotation, now we have the same start to our molecule here. Remember, this was 2, that substituent there. So number 1, which was this isopropyl group, was on the normal bond, but now it's going to be on the wedge. There we go. The CH3 on a dash is now going to be on this normal bond. Make the wedge a little wedgier. There we go. So that's a CH3. And the hydrogen is on a dash. There we are. So now if we make our Newman projection as before, we're going to have the isopropyl group on top, the ethyl group on the left, and the CH3 group on the right. 1, 2, 3 in priority, remember, which means that we go counterclockwise. So that should be R. Okay, so we've determined that the CIP configuration, it's R. Now we just need to determine what the name of this molecule is. So, and you can do this either, you can do the configuration first or do the configuration last if you want in the IUPAC naming. I chose to do it first this time, but you can always do it last. If you solve the rest of the name for this molecule first, so let's redraw it. This is probably what you came up with. So we have to first assign the parent chain, right? And doing that, we have 1, 2, 3, 4, 5 carbons. So that's a pentane. Okay, then we need to identify substituents. There's a 1CH3 and another CH3. All right, so those are both methyls. And there are 2 of them, so that'll eventually be dimethyl. And we need to identify the locant, or the location of each substituent, which means that here we have either 3, 4, or 1, 2, 3, 4, 5, either 3, 4, or 2, 3. And I think we need to choose 2, 3 because we need the lowest number, 2, 3 dimethyl. So we have, I'm going to write that or type this, that way it's a little neater. So we have 2, 3 dimethyl pentane. But the question is, where does our CIP nomenclature go? And it goes right in the front before everything else. We put it in a parentheses. And that's going to be 3. Oh, it's not R, it's S, isn't it? That's silly of me. 3S, because it goes counterclockwise, so it's S. Sorry for that mistake there. 3S, 2,3 dimethyl pentane. And those are the skills that you're going to need from section 3.5. You need to be able to, again, identify the number of chiral carbons on a molecule. You need to be able to assign the CIP configuration of chiral carbons in a molecule. And you need to also be able to develop an IUPAC name for each molecule too. And if all of this seems really complicated, and that's okay if it does, because it's a new system and a new series of identifications and problems we're going to solve. A professor out of UCLA, his name is Neil Garg, him and his team developed a cool gamification way to be able to find the configuration of molecules. If you go to rschemistry.com, as you see here, you can find a very nice little tutorial for how to do this correctly every time. So let's learn. We'll just choose an easy molecule. Let's restart because I've done this before. I like to play this game sometimes. Okay. Oh, cool. We're going to learn about a molecule that we use to prevent and treat HIV. So in this molecule, in this chiral carbon, the one that is starred, we're going to assign first priorities, right? So I guess number 1 priority is the one attached to oxygen because it has the highest molecular or the highest atomic weight. The number 2 priority is the nitrogen because it has the next highest atomic weight. We know that number 4 is the hydrogen because it has 1, and carbon must be 3. So even though this molecule looks very complicated, we were still able to assign the priorities pretty easily. All right, so then now we're going to make our Newman projection. So the hydrogen's in the back already, so we don't have to worry about doing any rotation. And it looks like number 1 is on the bottom left. Number 3 is in the bottom right, and number 2 is on the top. So would we call that R or would we call that S? To me, it looks like we are rotating clockwise, so it looks like that should be R. And we did it. We got the answer correct. So you can play through this and hopefully learn while also playing a little game how to assign the CIP configurations yourself manually. So this has been section 5.3.